Welcome to the video on differentiation. Differentiation is used to calculate rates of change, and these rates of change have important uses within engineering. Take the graph y equals 2x. If we compare this equation with our general straight line equation, which is y equals mx plus c, we can see from the x terms that the gradient, or m, is equal to 2. And we can do a similar thing with any straight line of any gradient. However, what do we do when we have a curve? Take the graph of y equals x squared. With this equation, we have no general equation of the curve to compare it with. So in order to obtain the gradient at any point, we need to do this process which is known as differentiation. And this is done as follows. First, we need to isolate the term in x, which in this case is x squared. And now, with this term, we multiply it by the initial power. And then the next step is to reduce the original power by 1. And there, x squared has been differentiated to 2x. What we've just done is differentiate y with respect to x, which is denoted as dy by dx. So we can just set that to equal 2x. Polynomials can be differentiated in a similar way to single terms in x, and this is done as follows. Take the equation y equals 3x to the 4 plus x cubed plus minus 2x. If we jot these terms down below like we did before with the single x term, we can go through step by step. So multiply through by the 4, reduce by 1 to 3. Multiply through by the 3, reduce the power to 2. And then multiply simply by 1, and then reduce x to the 1, which isn't shown, to x to the 0. And this simplifies to 12x cubed plus 3x squared, and then x to 0 goes to 1, so that becomes minus 2. And then we've got the function which is equivalent to the gradient of this first equation here in terms of x at any point along the curve. The use of this function here is that we can evaluate the gradient of this at any x value of our choosing. So if we wanted to find the gradient at x equals 2, we simply use this equation here. Just sub in x equals 2, so it would be 12 times 2 cubed plus 3 times 2 squared minus 2. And that is equal to 106, I think. But essentially that's the important part, and you can insert any x value into this equation here. We can also use this function here and set this to equal 0, basically saying when the gradient is 0, finding out which x value that is at. And that helps us to evaluate areas on the graph which are known as stationary points, and we'll look at that in a later video. Okay, so what if we had a function like y equals x cubed sine x? Now, this certainly isn't a straight line, and although it's a curve, we don't know how to differentiate this term here because it's not a standard term as a power of x. So to continue with the example, we just need a quick look at trigonometric functions. We can say this is y and this is the differential, which is dy dx, and this is sine x and cos x. And these two, this is just calculated results, just simply equal cos x and minus sine x. And these are standard results that you will use all the time whilst differentiating. However, that's just not all we need. For this particular one, we have a product of two separate functions. So we do need additional formulae. The formula we use is called product rule. And the product rule looks like this. Where u is one of these functions, it doesn't matter because this is linear, and v is the other one. So if we say, for argument's sake, u is equal to x to the 3, and sine x is equal to v. We can then set this problem out methodically in order to solve dy dx. And I do it as follows, a bit more space. We can just write out u equals x cubed, v equals sine x, du dx equals 3x squared, and the v dx equals cos x. And then we can just use these values, plug them straight into this formula to get dy dx directly, and it's quite a neat way of setting it all out. So I can say dy dx equals x cubed sine x plus cos x plus sine x times 3x squared. We can just tidy that up, and eventually it gets to x squared x cos x plus 3 sine x with a bit of algebraic tidying up. And that's how we evaluate products of two separate functions. What if, instead of having the product of two different functions, we had a quotient of two functions? Say one function was divided by another. Take y equals sine x over x squared we need a different rule, and rather than the product rule, this is simply called the quotient rule. And this is written out as follows. v squared. However, in this rule, rather than it not mattering which function you assign to u or v, it is imperative that you call the denominator within the equation v, because you divide by v squared, so it always has to remain the same. And so it's a similar process. I like to set it out neatly. U equals sine x, v equals x squared, just du dx equals cos x, dv dx, as we've done before, is simply 2x. And then comparing with the rule we have here, you can write this out directly as before. Equals x squared cos x minus sine x times 2x all over x to the 4, which is just x squared squared. And then this simplifies all the way down to x cos x minus 2 sine x over x to the 3. That's just the algebraic legwork done for you there. It's an easy enough simplification. Okay.